So now we're going to talk about whether or not a curve is smooth. So the parametrization of the curve represented by this vector valued function r of t is f of ti plus g of tj plus h of tk is smooth on the open interval I if f prime, g prime, and h prime are continuous on I, and r prime of t is not the zero vector for any t in I. In other words, there's no place where the curve just kind of stops. Remember, r prime would correspond to velocity. So there's no place where it would stop. So here's an example. Find the intervals where the epicycloid curve C is smooth. Note an epicycloid, if you've never heard of that before. It's probably not an everyday dinner table word. It's made from rolling a small circle around a bigger one. The curve traced by a point on the smaller circle is an epicycloid. So C is traced by the vector valued function r of t equals, I'm just giving this to you, 5 cosine t minus 5 cosine, minus 1 times cosine 5t I plus 5 sine of t minus sine of 5tj. Our concern is the places where r prime is 0, since f prime and g prime, the derivatives of these trig functions, are continuous everywhere. Not just because of trig functions, but because derivative of sine and cosine in any linear combination of sine and cosine is continuous everywhere. So this is our vector valued function r of t. And so what's the derivative of that r of t? Well, if we took the derivative of 5 times cosine t is going to be negative 5 sine of t. The derivative of cosine of 5t is 5 times the sine of 5t. This 5 comes from the derivative of the inside part, just like it always did in Calc 1. So the derivative of 5 sine of t is 5 cosine of t, and the derivative of sine of 5t is 5 times the cosine of 5t, so with a negative sign that was in front of the original problem. So here is our derivative of our vector valued function. Now, we don't want either of our component functions to be 0 at the same time. So, by inspection, I admit that was cheap. You can see that if t was 0, this function is 0. By inspection, you can also see that if t is 0, this function is 0, so we've got ourselves a bad point. We've got ourselves a bad point when t equals 0. Notice if we moved to pi over 2, see, since sine of pi over 2 is 1, this is negative 5, and sine of 5 pi over 2 is the same as sine of pi over 2, since it's coterminal, and so that's also 1, and then times positive 5, so that's 0. Now notice cosine of pi over 2 is 0, so that's 0, and cosine of 5 pi over 2, since it's coterminal, is also 0, so pi over 2 gives us an ugly spot. Now notice that pi also gives us an ugly spot because both of these are 0, and this one is negative 1, so that's negative 5, and this is 5 pi, so it's also negative. Cosine of 5 pi is also negative 1, but it's times negative 5, so the negative 5 and the positive 5 cancel out. And again, at pi we've got a problem, and you can probably see there's lots of places beyond that where the r prime is equal to the 0 vector, 0i plus 0j, and when that happens the curve is not smooth, but it is smooth everywhere else. On the interval 0 to pi over 2 open interval, I should say, because not at pi over 2, and then also from pi over 2 to pi to 3 pi over 2, etc., which is just on one cycle through 0 to 2 pi. The graph is smooth and unsmooth at the axes intersection points. And here's a picture to show you. See, smooth here, but not here. Right there, there's a point where it's not smooth. Of course, that's at pi over 2. And then when we go over to pi, we got another point where it's not smooth. See, it's not a point of differentiability there if it was just a regular graph. So it's got a, I think the fancy word is, it's a cusp. And here's another cusp. At 3 pi over 2, here's another cusp at 2 pi, and of course the epicycloid is just going to keep rolling around and around there. Some things to note about this epicycloid. I guess if I were to change a little bit about this, if I change that to a 3, see, then suddenly you see we don't get quite high enough in the x direction, and then we pick up this little teeny loop here. So it's kind of cool when that happens, but that's not an epicycloid. And if we made this 4, see, it's not an epicycloid then either. But what you do have here, you know, it might be smooth here. I can't tell unless I zoomed in a little bit. This doesn't look smooth out there, or here. This might be, but certainly it's not smooth at that point. So I just wanted to show you an example of something that's not an epicycloid, and so you could compare. But here we have here, and here points where the graph is not smooth.